Folks, in this video tutorial, I'm going to discuss a few items about the normal contact behavior in a finite element calculation. And because there seems to be some confusion about some of the terminologies used. And also, it is intended for, this tutorial is intended for people who are either 3D experience users or they're Abacus CAE users and they're transitioning to the 3D experience via the fact that the solver in 3D experience is actually the Abacus CAE program. Now, uh, what I usually do is I select problems that are done by other YouTubers and they are done in the CAE, Abacus CAE, and replicate the steps in the 3D experience to show people that the interface is completely different and it is not that one who does Abacus CAE can automatically sit behind a monitor and or terminal and do the same problem in the 3D experience. It's part of the fact that the solver is the same. Now these are the icon. These are the this is the action bar from the 3D experience interface, and it involves the concept of interaction and all the stuff that you need in the in contact. Now I'm going to be and it applies. The stuff that I'm going to talk about applies to both the surface which means surface-based contact interaction and general contact interaction. However, I will concentrate primarily on this contact property because that's where the normal behavior and the tangential behavior are described. Okay, so here's a dialog box. Here's a dialog box for contact property. And notice that the two items here, one is friction, which is tangential friction. I'm not really interested in this, but the other one is called closure and separation. Okay? And when you look at the possibilities, there are three of them, namely hard contact, tabular contact, and experimental. Uh, exponential, not experimental, exponential. So let's look at the problem. Suppose you have a block here on the right-hand side that is the bottom of it is fixed. And then there is another block on the left side which is being pushed to the right, and there is a gap between them. Now, needless to say that you keep pushing and there won't be any interaction, there won't be any pressure build up between the two, obviously, until that gap becomes zero. It's only when the gap becomes zero that actually the the block on the left has in fact is in fact contacting the block on the right, and there is a contact pressure between them. Okay, so that is the what we expect from physical observation. I mean, this is called hard contact. By the way, some people instead of gap they call it clearance, but it's the same thing. Okay, so here's the situation. If you look at what we just discussed, is that when the gap is not zero, for example, we're calling it on this side gap negative. When the gap is negative, there is no pressure because the block on the left, has not even reached the guy on the right, the block on the right. There is no pressure between them. However, when the gap becomes zero, the clearance becomes zero, it means that the block on the left is actually has reached the one on the right and it's going to be pushing on. So there is going to be a pressure buildup between the two. Now, notice that on this side, which is called overclosure, it's never going to happen. In other words, there is no way that this guy can actually penetrate through the block on the right. Okay, that's true. So physically, this is what happened. This is called hard contact, and that's what physics says and everyday observation says. Now, the problem is we may pretend that actually the thing on the right happens. Okay, and that is called soft contact, and I tell you why. Okay, physically it's not possible. However, because there is a sudden change in pressure from nothing to whatever it happens to be, then this may cause a lot of convergence properties. Okay, that's why people allow this behavior not to be a sharp jump, but a gradual change, which means that incidentally, if it's a gradual change to the right, it means that physically it's not possible. However, in order to solve the convergence problem, so they use a numerical trick. In other words, instead of this, they say, okay, maybe this is the way the pressure should be built up. But of course, physically, we know that's not possible. But this works. I mean, if your set of equilibrium equations do not converge to what you're expecting, then whatever makes it work is going to be used. So this is one way. This is called the exponential model, or you can actually give numerical data here and gradually build this up instead of suddenly jumping to a non-zero value. Gradual build up. Now, let's see now. Obviously, here you give data points. Basically, either there is no experimentation here because it's impossible. This has nothing to do with experiment. This has nothing to do with physics. Okay, but here you give a two parameter. In other words, the gap where the pressure was zero, and then it starts building up, and then this pressure P naught. So if you give it these two in an exponential model, you can actually do the whole thing. Now, I want to say also I'm going to make a few comments before I do an example, a few comments about this non-common terminology in contact. Suppose we have a aluminum block here and we are pressing with a punch against it, which is made out of steel. So the punch up there is hard, it's steel. The block down here, which you want to reshape, is soft and it is, let's say it's made of aluminum. Okay. I call this punch primary surface, M surface. And I call the block that we want to change shape secondary surface. Primary, secondary. M surface, S surface. Steel, aluminum. A couple of things that you should know is that if you have to make these choices, the steel block on the top must have the coarser mesh, and the aluminum block down below, S surface, or secondary surface, must have a finer mesh. Now, remember, the nodes of the softer piece, which is this, slide on the boundary of that primary surface, on the punch. The nodes of the aluminum actually slide on that. This is something to keep in mind. So something like this is not possible if we pretend that this thing, the one with the green dot node, is the primary surface, and the one with the red nodes is the secondary surface, namely aluminum, because the red nodes slide on the boundary of the primary surface. Something like that may happen, and this is not good. That's why you want the S surface, the secondary surface, to have a lot of nodes, so that something like that will not happen. This is not okay, and therefore keep in mind that the coarser mesh must be on the, think about it as the punch. Okay. Here's the guideline that most FEA software, including Abacus, which is the solver in the 3D experience, suggests. The primary surface, M surface, must have the coarser mesh. We already said that. The primary surface, M surface, must be bigger in size, big punch basically. It's a physically bigger in size. And the primary surface, M surface, must be stiffer, okay? So, for example, steel is stiffer than aluminum. Of course, there is also geometrical effect that has to be looked at. That's why I'm saying stiffer. I'm not saying softer or harder. Now, if not all three of these can be accommodated, then precedence was given in the first two. Okay, so at least these two. Okay, or any two that obviously works. So once again, exponential model, tabular model, physically not possible, but you may need it in order to resolve convergence issues or to overcome divergence. Okay, so let me do an example. This example comes from a YouTube reference that I'm having down below. I'll show it to you down below, but it'll give you an idea of how things work in the 3D Experience platform for this particular problem. So we have a block here, which is clamped at the bottom, and we have a block that's being pushed to the right, and there is an initial gap of 0.5 millimeter between them. You can see that, okay? Both are made out of steel for simplicity, and I'm going to measure it with 4-noded element and 1 millimeter in size. And those parameters, uh, G naught is 0.3 millimeters, and P naught is 200 megapascal. And there's a friction coefficient of 0.1. Now, what this means is that if you push to the left, nothing is going to happen. There won't be a pressure. But as soon as the gap goes to 0.3, as soon as the gap becomes 0.3 millimeter, pressure builds up, in spite of the fact that they have not contacted each other. So that's what really this means. And when it closes, when this reaches there, the pressure maximum, the pressure is going to be 200 megapascal. Okay. So basically, this is what we're doing. And this comes from the reference down below, and that fellow does this problem with something very similar to it with the uh, Abacus CAE program. So by watching this video on how I do it in 3D Experience and the Abacus from this gentleman, you can see how the differences are as far as the workflow and interface and model building. Okay, so let me go ahead and make it. So here is the 3D platform. I go to assembly. We're going to make an assembly because this is a contact problem. It must involve an assembly. And I'm going to right click, insert a block. I'm going to do the big block on the right first. So block, 3D part. I'm going to change this thing, name of this thing to big block. How about that? Properties to big block. And big block. Okay, let's make it. Double click on that vertical plane. I will sketch. I'll sketch a rectangle. The size of this rectangle, I believe here is 30 millimeters, and this is 20 millimeter. Exit. And let me pad it by the calculation that's done by that YouTuber is for plane stress, but we don't have two-dimensional elements, plane stress and plane strain in 3D Experience. So what I'm going to do is I'm going to make it just one layer and not put any restraints on the two sides. So essentially it becomes a plane stress problem. So I'm going to pad this thing. I'm going to pad it by 10 millimeters. There we are. So this is the big block on the right. Okay. Now, why don't I put some material on it? So tools, apply material. What do I make one? Create material, and I'll call this thing steel block October 16, 2023. Okay. And we're going to input the properties in just a minute. Once it's created in the database, it's going to be the same material for both of them. Steel block October 16, that's what it is. apply on this. I don't need that anymore. Let's go and input the properties, steel block, double click. So under structural, under Abacus multiphysics, mechanical, elasticity, elastic, 200,000 gigapascal, or 200,000 megapascal, or, or 200 gigapascal, either one, and Poisson ratio 0.33. That's all we need. All right, so let's go ahead and make the block on the right, all the way to the top. Right click, insert, 3D part. We're going to rename this thing to be a small block. Properties, small block, and small block. Okay, let's go make it. It's another box like that, and I'll place it on the right side, half a millimeter away from it. So on that vertical plane, I will sketch a rectangle like that. The size is, this height is, I believe, 15 millimeters. Yep, and this side is 20 millimeters. Okay, let's put a gap of 0.5 millimeter between the two ends, between the two lines here. So the distance between here to here, 0.5. Okay, exit, pad it by 10 millimeters, just like the other one. And you can see that there is a gap of 0.5 millimeter between the two. I just want to check, make sure that that gap is in fact 0.5. Yeah, it looks like 0.5. Good, good. Exit. And we apply the same material on this. We know how to do that. Tools. We already have the material made, so browse it, material browser. There it was. A steel block, October 16. So apply on the second piece. And we're going to close that. We don't have to input it because it's already there. It's the same material as above. Okay, very good. So all the way to the top, all the way to the top, and let's apply, let's mesh it. So we go to structure model creation, empty FEM. Both of these parts, we want them to participate. So it's telling you that there are two parts here. Which ones do you want to participate? Both of them? All right. So go to meshing. Let's do the big block first. So here is this a very nice sweep 3D mesh. These are going to give you 4-noded or 8-noded break elements basically. So there, and the size 1 millimeter, and one layer through the thickness. One layer through the thickness. I mean, you can make it 10 layers. It really doesn't matter. But I'll make it one layer because that's all I need. Good. And then we say OK. And these are linear, by the way. You can see that. Now we're going to do properties of this. So we go to properties, a solid section. You select this part body, and the steel block material is selected. You do the same thing on the other one. Go to mesh. Once again, sweep 3D right there. Same size elements, same number of layers. Very good. And then properties, or where is that? Properties, solid section on this part. Same material. Good. Why don't we save the model, and now we're going to go to our structural scenario creation. Remember, this one has some basic licenses. This one, if you want, for example, do explicit dynamics and things like that, you don't have it there. You have it here. You have implicit dynamics there, but anyway, we're doing a static problem. That's good enough. You click on that. You're doing a structural problem, and the mesh is already created. Select the mesh from finite element model from through this pull-down menu. Okay, good. Let's go to procedures. It's a static step. And because I want to have several, I don't want to do it in one shot. Remember, linear problems, static problems, you can do it in one shot. But because I want to see the the kind of the movement of this block towards that, I'm not going to uncheck the nonlinearity. See that? Include geometric nonlinearity. There is none here, but I will put a initial time increment of 0.01 and a maximum time increment of uh, uh, let me make it yeah, point one. Okay, point one. Now you say okay. All right. Notice that these are both green check marks, which means that uh, we're ready to go. So let's go ahead and apply our boundary conditions. The bottom of the big block is clamped, so select the clamp from here. Actually, let me clamp. The only degrees of freedom are, of course, translations. Okay, so we say fine. And this one is can move in the y direction, so I'm going to say okay, fix displacements, allow motion in the y direction, but for x and z I make it 0. Essentially it becomes a roller. Okay, good. Now we want to push this thing to the right. Right now the gap is 0.5 millimeter. So we want to push it to the right through a displacement. So we're going to try to bring them in contact with each other. So apply translation on this side in the direction y by the amount 0.5 millimeter. You say okay. Good. Now we create the interactions. Okay, so click on the interactions. First, the friction coefficient. That friction coefficient really was unnecessary for the YouTuber that I showed you to do it. But anyways, since I want to go do exactly the same thing, I'll click on it. Friction, specify friction, and it's going to be point 3 in the slide. Wait a minute, what is it? Not point 3, point 1. Sorry, point 1, point 1, point 1. Okay, good. And this is done. So now we go and do the over closure and separation. Specify. First, we do hard contact. In other words, there should not be any pressure buildup until that guy reaches this. Okay. So first is hard contact. In other words, we're doing not doing this. We are doing this situation. Okay. So hard contact. So let's yep, and that's pretty much it. Say okay. Now we do a this is just specifying the properties. Now we're going to do surface-based contact. So the main surface is, when remember those guidelines that I gave you. This uh, uh, in this particular problem, it really doesn't matter. Okay. However, okay, so I will do because the density of the mesh is the same for both. Okay, so I took the surface of the big block as the primary surface, and the secondary surface is the surface of the small block. All right, and for contact uh, contact properties is contact property 1, the one that I just created, right, with the friction coefficient. Remember friction coefficient? You say fine, good. And let's do a quick save, and we're going to run. So No pressure buildup will be between these two surfaces, between these two parts, all the way until the analysis runs, because I'm pushing this thing by zero point 0.5 millimeter and the gap is zero point 0.5 millimeters. So there should not be any, with a hard contact, there should not be any pressure between them. So let's go ahead and do that. We go to simulate, do a quick model check to make sure I didn't forget anything. That's good. Simulation check once again to make sure that I didn't forget anything obvious. And then once that's done, which is going to be very quick, then I'm going to run it. This is a linear problem. It's going to go through very quickly. Okay. Some warning here. No big deal. Almost done. We haven't run it yet. This is just simulation check. Okay, that's done. And now we're going to run it right there. And nothing exciting is going to happen. This block on the left is going to move to the right, move, 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 move. Once it reaches the end, the program stops because we have reached the end. No contact established. Contact pressure between the two pieces is going to be zero for sure. So this is a hard contact. The only thing that's physically possible. So, okay, now it starts running and we can monitor the progress by looking at the iterations. It's going to be very quick. Analysis failed due to error. So let's find out what the error was. Okay, obviously the analysis failed because of an error, but okay, that's fine. But maybe we can see what happened up to this point. Okay, so we can say close. We can say close. Of course, it didn't complete, right? But we can go to the result, and it's going to tell us what happened here. So if you go further down, this is where we started, and then you can see what's going on. I have a feeling that the displacement that I specified here was not correct. I was going to say 0.5 millimeter. In all likelihood, I put down 0.5 meter. You can see that, I mean, obviously it goes crazy after a while. It can't converge because this is not the way it's supposed to be. So let's go ahead back here, apply translation. Apply translation. Oh yes, 0.5 meter. So I'm going to change that thing to millimeters, say okay, and then run it. I bet we're not going to have that problem. It's good to run into issues like this so that we can look at it together and find out what the problem may be. Because in spite of the fact that the program does not run, at least it gives us the opportunity to see up to the point that it ran what happened. And when we looked at the result, we noticed there's a lot of deflection of that block on the left. And obviously the reason was the fact that I put down 0.5 meter is 500 millimeter displacement. It's not going to converge, you know that. The whole thing was only 20 millimeters, 30 millimeters long. Okay, this is going to go through, guaranteed. But remember, this was not the issue. We want to look at the contact pressure and see what happens. There should not be any pressure between the two pieces because it's hard contact. We pushed it by half a millimeter. The gap was half a millimeter. There should not be any contact. And you can see that it finished. Good. We can look at the results. Good. Let me close this. Okay, so let's go back to where we started, right there. This is when we started, right? So let's keep going. So push to the right. Don't let that thing fool you. Look at the numbers to the minus 12. This is minus 13, minus 12. These are all zero. For all practical purposes, they're zero. And they should be because there's no contact between them. Then now this is where it reaches still almost zero. All right. So now I'm going to change it to exponential model. The only thing is that I would like to create a group here so that I can see only the contact pressure. Even now I can see the contact pressure. See that if you change this thing to contact pressure, but it gives it to me, and these are blocking. I want to see just this face. Okay, so in Abacus, you go and create a set, and then say that show me the stuff on that set. But here, what I'm going to do, I'm going to click on this. I'm going to say display group, and I'm going to make one. What is that? Create a display group, and I'm going to select this and say OK. All right. Now, when I go and look at the plots, look at this plot, for example. Let me double click on this. Hang in there. Let me double click on contact pressure. Okay. Okay. So cancel that. Sorry. Display group 2, that's the one that I created. Show me the rest of the stuff, this rest of the stuff. Okay, but invert. Okay, there we are. Okay, good. So I'm plotting here. You can see that contact pressure. At the very end, the very last step, contact pressure, all zeros. So now we're going to do the following. Let's go ahead and let's go to our, okay, so let me go to scenario. Okay, good. Go to the contact property, over closure and separation, not hard contact, exponential. I need to input those two values. So 0.3, that means no pressure until the gap becomes 0.3 millimeters or less, and the maximum value is 200 megapascal. So basically, I'm giving you two pieces of information, P0, G0, and P0. Okay, so G0 and P0. And then we say OK, and then all we have to do is to run it. So there won't be any pressure until this block on the left advances by 0.2 millimeters. The gap becomes 0.3, and then the pressure becomes non-zero. Okay, so now it's going to run. Remember, I plotted the contact pressure, but because it was between two surfaces, I could not see it. So I had to go and create in 3DEXPERIENCE called group, display group, and I just showed it on the display group, okay? In Abacus CAE, you have to create a node set probably and then say, show it to me on that node set. But yeah, this is almost done. You can see that finished. All right. Let's close this. There we are. Let's go at the very beginning, right there. And let me make this thing smaller so that you can see the value of the pressure on the right side. Okay, so as the block is moving to the right, no pressure until it reaches, advances by 0.2 millimeters, so that the gap becomes 0.3. And now pressure begins to build up. You can see that. Now this is still have not contacted it yet, but the pressure builds up, and this is exactly where the surfaces contact each other, and the maximum was declared to be 200 megapascal. It is 177. Okay, so let me show you one more time. Let's go here and let me deactivate this, activate one Mises stress, and I want everything. So show me everything. Show me everything. Good. Start at the very beginning. Very beginning. Make this thing smaller. This is the von Mises stress, okay, in the two parts. Nothing. These are nothing. Look at the power, 10 to the minus 12. Nothing, 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 nothing. This is when it actually becomes to within 0.3 millimeters of each other. There's a gap there. You can see that. There's still a gap. And go past that, still no contact. However, the pressure begins to build up. And that's exactly what that exponential model is, or the non-physical model is. Okay? And that is needed in case there's a complicated, contact and things don't converge. You may have to go and use tricks like this. Yep. Hard contact is the only thing that's physically possible, but may not converge. All right, folks, I hope that this helped you a little bit on at least seeing how things are done in 3D experience, and a little bit about this issue of hard versus soft contact.